Okay, so we are now on to Applied Year 2, chapters 5 and 7. And the reason I've split it in this way is chapter 5 covers everything to do with friction, and then they do some kind of applications of it in chapter 7. And for me, it just makes sense to have these two things combined. And that's actually also how I do it in the playlists as well. Now, there's quite a few pages on this. We've got 4 slides of questions, so let's dive straight in, which is to do with angled forces and friction. And so to begin with, I want to talk about what we do if we now have a force that's acting at an angle. And you should know this. We can resolve an angled force into its perpendicular component. So this is the size of the force, this is maybe the angle that it's moving at, and we know you can just split this using sine and cos. So the thing that is going to be adjacent to it would be cosine, because we know that cosine goes with adjacent from SOHCAHTOA, and the thing that's opposite is going to be f sine theta, because we know that sine theta always goes with opposite from SOHCAHTOA. And sometimes people are a bit confused about the direction of the arrows. You can see this arrow is going, as my sort of laser is showing, which is to the right and up, so that it's kind of mimicking that same journey of starting here and finishing here. Now, as before from year 1 forces, if it's described as being in equilibrium, which means that it's either not moving or that it is at constant velocity, then the forces are balanced. If it's accelerating, this is where the forces are imbalanced, and obviously we use F equals ma, and I usually resolve in the direction that it is moving in or accelerating in. Okay, and then when we talk about friction, friction is an interesting force. It resists motion, so whichever way it is going to move in or it is currently moving in, it is going in the opposite direction to that. The formula for friction, for the maximum value of the friction, is mu r, where mu is the coefficient of friction and r is the normal reaction. When I do friction, I often do a little r next to it so it doesn't confuse us with like F from F equals ma. And the value of friction can be anything between 0 and its maximum value, which is mu r. And what it does is it takes a value to counterbalance opposing forces. So it doesn't always equal mu r if it is not like at that kind of limiting equilibrium, and we'll demonstrate that in an example in just a moment. Friction does reach its maximum though for these scenarios where it is in limiting equilibrium. In other words, it is just about to move or it is about to slip, where the velocity is constant because it is actually moving, so friction has already got to its maximum, or if the particle is accelerating as well, that's where friction will have reached its maximum. And we'll use this exam tip during these questions. We're going to redraw a force diagram. It can often aid our thinking and help us to reduce making silly mistakes. So this one is probably not like that exam style. It's more to kind of re-examine the concept of friction and angled forces here. But let's have a look at these 3 different scenarios that we're going to analyze for a particle P, which has mass 6 kilograms and starts at rest on a rough horizontal plane. P is pulled by a horizontal force of magnitude q newtons. The coefficient of friction between P and the plane is mu. And given that mu is 0.25 and q is 20, fully describe the motion of P. Now, I've said fully describe the motion of P because if I actually asked the question I wanted to, it might kind of give away what I was saying. And you'll see what I mean when I do this. So I'll do a quick diagram. It has a mass of 6 kilograms, which means I can immediately say that it has a weight of 6g. And it has a normal reaction R, which we're going to need to use, and it is being pulled by a horizontal force of magnitude 20 newtons, because that is Q that we've got there. And because we've now got this mu, we know that there's a rough sort of force that's going on here. Let's actually calculate the maximum value that this friction can be that we've got over here. And I'll come back to the diagram in just a second. So to begin with, it is not moving in the up and down direction. So I can actually just resolve in the up and down direction and just say that R is equal to 6g. Now I'll do my calculation for the friction, which is the friction max. But if you don't write friction max, if you just write friction, that's absolutely fine. I often just write friction. That is going to be equal to mu r. You often get a mark for that. Mu is 0.25 that was told to us in the question, and r is 6g. So the maximum thing that the friction can take is 6 times g times 0.25. G is 9.8. Which is 14.7. So actually, it will have reached its maximum value that we've got over here because of the fact 20 is bigger than 14.7. So it can't oppose that 20 anymore. It's going to go right up to its maximum value, which means that we now know that it is going to accelerate to the right. So I'm going to resolve going to the right, and I'm going to do that using F equals ma. This is me trying to fully describe the motion of P. I want to actually tell them it's going to accelerate and how much it will accelerate by. So this F in the formula, remember that's the resultant force, that will be our 20 minus 14.7. And that is equal to its mass, which is 6, times by its acceleration. So all I need to do is 20 minus 14.7, divide that answer by 6, and we get that the acceleration is 0.883 meters per second squared, and that is to 3 significant figures. You could also do it to 2 significant figures if you wanted to. So to describe the motion of P, I will say it accelerates in the direction of the pulling force with magnitude 0.883 meters per second squared. Okay, let's see what changes in part B. We're going to introduce some angled forces. It says, given now that Q is applied at an angle of 60 degrees above the horizontal and that the magnitude of Q and mu remain the same, fully describe the motion of P. So it's the same kind of diagram, apart from this 20, the Q that we have, is being applied at an angle of 60 degrees above the horizontal. So we're still going to have the normal reaction. We are still going to have the 6G, and we'll come back to this. We know there's going to be some resistance to motion. We just need to know if it's kind of reached its maximum or not. So this force, this 20 and the 60 here, we know this is going to need to resolve. So I'm going to resolve it into these two directions. Along the bottom is adjacent to the 60, so it's cos. Along the side is opposite to the 60, so it is sine that we've got here. And this is sometimes where redrawing a diagram can be helpful, and you'll see it might get more helpful in sort of the more challenging questions. So I'll put the R, and the other force that's going up is the 20 sine 60. And then the force that's coming out to the right is the 20 cos 60. Notice how I'm not doing another 20. I've split it into two, so I'm not going to put another 20 anywhere else. I'm going to have my 6G, and then I'm going to have this frictional force that's coming out to the left. Now, interestingly, people often just think, oh, the value of R is always just the weight. But now I'm showing you the value of R is not just going to be equal to the weight because of this bit that we've got here. So when I do the resolving in the up and down direction, the R plus the 20 sine 60 is going to be equal to the 6G, which means that R is 6G minus 20 sine 60. So that's 6 times 9.8 minus 20 sine 60. And I get 41.4794, blah, 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 like this. So if I wanted to now calculate the value of the maximum thing of the friction, it's mu r, which is 0.25 times r. So I'm just going to times that by 0.25 that I got my calculator, which is 10.3698, like this. So now I actually know I can just do a comparison between the 20 cos 60 and the f that we've got here. So let's just quickly work out what 20 cos 60 is. 20 cos 60 is 10. Okay, so the maximum value that the friction can take is 10.3698, meaning that it is not going to go to 10.36. It would be so weird if someone is pulling it to the right and then it starts moving to the left. So actually, friction will not take its maximum value. So I can say as 20 cos 60 equals 10, friction will not take its maximum value. In fact, the friction will just counter it. So the friction will be 10 newtons. So the friction is going to be 10 newtons. And the, what is it, a box or a particle? A particle. And the particle remains at rest. Okay? So it didn't have enough pulling force here. Now it's only going to counteract the 10. It doesn't reach its maximum. It's not going to move. Now I haven't really created much space for myself here. I wonder if I can sort of squeeze it in this last part that we've got down here. I'll have to do a nice small diagram for this. Given that mu equals 0.25 and that Q is now applied at an angle of 30 degrees above the horizontal and that P is in limiting equilibrium, find the magnitude of Q. So the only difference now is that it's being applied at 30 degrees above the horizontal. So we still have the R. We have the Q. We're trying to find the magnitude of Q in this case. We have the 6G. That's 30. And because it's going to be in limiting equilibrium, we're going to say there is going to be some kind of frictional force that we've got over here. So the two forces, very, very similar diagram to before. This will be a Q sine 30 and a Q cos 30. I'm not really going to need to draw an extra diagram of this. It's pretty simple. But I will say that it is in limiting equilibrium. That tells me something, right? Limiting equilibrium When something is in limiting equilibrium, friction is its maximum. So this friction that I've got here, I could actually replace with mu r. I can actually replace it with 0.25 r that we've got here. Limiting equilibrium, friction equals mu r. So all I need to do now is say the forces up equal the forces down, etc., etc. So the r, goodness, that was a big highlight. The r and the q sine 30 equals the 6g. And the q cos 30 equals the 0.25 r. Looks like we've got a pair of simultaneous equations here. So resolving it in the up and down direction, it's in equilibrium. R plus q sine 30 equals 6g. And resolving in the left and right direction, 0.25 r equals q cos 30. Okay, I think probably the best way to solve this is just to make r the subject of this top one and then substitute in. So r is 6g minus q sine 30, and I will substitute that r in here. And then maybe I'll have fitted it all in one page. So 0.25, 6g minus q sine 30 equals q cos 30. Okay, so 6 times 0.25, so this is a 1.5g minus, I'm actually going to do the sine 30. Sine 30 is a half. A half times 0.25 is an eighth, so this is minus 1/8 q. And q cos 30, that's going to be root 3 over 2q that we've got there. So my final thing is to solve this equation by doing root 3 over 2 for the q that we've got there. I'll add on 1/8 to that. And so I get this. It doesn't really matter what it looks like, but it's 1 plus 4 root 3 over 8q. So when I solve this, I will do the 1.5 times 9.8 divided by that thing that I've got on my calculator. And we get that Q is 14.8 newtons to 3 significant figures there. Okay, so is that what we wanted to do? Yes, find the magnitude of Q. So limiting equilibrium, all the forces were balanced, and we knew the friction had taken its maximum value. Okay, now we're going to have a look at what happens with forces on planes. So for forces on planes, just remember that the weight is always vertically downwards. The normal reaction is always perpendicular or normal to the plane or to the surface. And this time you're going to resolve forces parallel and perpendicular to the plane. Previously we were doing vertically and horizontally. We're now going to be doing this parallel and perpendicular. But other than that, it follows pretty much the same pattern that we have here. So, a rough plane is inclined to the horizontal at an angle theta, where tan theta equals 4 over 3. Now, I always pause as soon as I've got to that stage, because if I know that tan theta is 4 over 3, usually you're going to want to find out sine theta and cos theta in a question. Now, you can do this on the calculator, or the way I always think about this is with a quick triangle. We know that this is the opposite and this is the adjacent. So the opposite is 4 and the adjacent is 3. When you do Pythagoras with this, we know it's a 3, 4, 5, 1. So sine theta is the opposite divided by the adjacent, by hypotenuse, which is 4 over 5. Might be more useful in decimal form. And that cos theta is the adjacent over the hypotenuse, which is 3 over 5, or in decimal form 0.6. Okay, so I did do a bit of a jump away from the question there. Always good to just do that at the beginning because you've got less to think about then. A small box A of mass 0.5 kilograms. Okay, I'm immediately going to put that weight on the diagram, which is going to be 0.5 with G, is held at rest on the plane by a horizontal force of magnitude 8 newtons, as we've got in this diagram. The force acts in a vertical plane, this should say, my typo error there, which I'll add back in, containing a line of greatest slope of the inclined plane that we've got there. That's really annoyed me, so I'm just going to put that in like this. All this sentence really means that this 8 newtons is exactly as it looks like here. It's not kind of like going into the page or out of the page or the screen. It is just kind of a sentence you can basically just ignore, but I did put it in because you'll see it in the exam questions. It then says that the box is on the point of moving up the plane and is modelled as a particle. Find the coefficient of friction between A and the plane. Okay, so we've done the weight, but we do need to add in the normal reaction, which is going to be perpendicular to the surface like this. We've been told that it is a rough slope that we've got here, and it's on the point of moving up. That means it's in limiting equilibrium, so that friction has reached its maximum. And if it's going to move up, the friction is going to be resisting that and come downwards. Now, you can just go straight in and call it mu r on the diagram, or you could call it friction. So I think we've pretty much got everything in terms of the forces labelled. We now just need to deal with the ones that are angled forces, and then we'll probably redraw a diagram. So for the 0.5g, we need to split it so that all of our forces are now going either parallel or perpendicular to the plane, which means that I need to split this 0.5g so that we've got a one that's perpendicular and parallel. The angle that we have here is theta. I won't go through the details of that, but I do go through that in the playlist. So this one would be 0.5g cos theta, and this one would be 0.5g sine theta because it's opposite the angle. And then we need to think about this 8 newtons. Now this 8 newtons, this angle that I've just done in purple, is also going to be a theta because of these alternate angles or z angles. And so I can split the 8 newtons into a force down and across. Obviously it's following the direction of that arrow, so it's going to go like this, and I'm still trying to do perpendicular and parallel to the plane. So this one would be opposite, which is an 8 sine theta, and this one is an 8 cos theta. Now, these new diagrams that I've been drawing like here, this actually came to me from a student in probably one of my first years of teaching. This is to Wahida Begum. There is no way that Wahida is going to be watching this video, but she is a maths teacher and she is one of my best students of all time, and she taught me this new diagram and I have used it ever since. So thank you very much to Ms. Begum, who works in Tower Hamlets as a maths teacher. So yeah, and it's great when an ex-student becomes a maths teacher. That always makes me very proud. Now I've got distracted thinking about my previous students, so I'm now going to just redraw this diagram, okay? I'm going to do these forces kind of coming upwards, coming out of the box, and then I'll highlight them to show that I've dealt with them. So we've got the normal reaction. You know, I could have drawn the box on its side, but I just find it easier to kind of do it like this. So I've dealt with the normal reaction. Now let's deal with the 0.5g parts that we've got. So I have the 0.5g cos theta, and then I have coming out of this way the 0.5g sine theta. So I'm going to just tick off that I've dealt with that one and that one, which is obviously the same as this one. And then I think I also need to put on the friction. It's quite easy to forget that friction, which is coming out the box. So I shall add on the mu r that we have. And then I've got to deal with the 8 newtons, which is an 8 sine theta down and an 8 cos theta coming up. So we have the 8 sine theta that was going down into the box, and that 8 cos theta, it's going into the box, so I just draw it still coming out of the box like this. And that means I've also dealt with the 8 newtons. All of the forces have been dealt with, and I've got a much more simplified kind of diagram. Now it's in limiting equilibrium, which means everything is completely balanced. So I'm just going to go straight in with my calculations. So I'm going to do resolving, I guess it's actually resolving perpendicular to the plane like this, in this sort of direction, but on my diagram it's these ones that are going up and down. So r is equal to 8 sine theta plus 0.5g cos theta, and I know these things here, so I can just type on my calculator 8 times 0.8 plus 0.5 times 9.8 times cos theta, which is 0.6, and I get that the normal reaction in this case is 9.34 newtons. Now I'm going to resolve parallel to the slope, and when I resolve parallel to the slope, it is still in limiting equilibrium, so these ones are all equal to each other. So now I know that 0.5g sine theta plus the friction is equal to 8 cos theta. So this means that mu times by r, which is 9.34, is going to be 8 cos theta minus 0.5g sine theta. 8 cos theta is 8 times 0.6 minus 0.5 times 9.8 times sine theta, which is 0.8, and that is 0.88. Which means my final thing is just to divide by the 9.34 that we have. And I come up with mu as 0.0942 to 3 significant figures. If you wanted it as an exact value, I think I have it as 44 over 467, but it's no need to have it as an exact. A rounded value is perfectly fine. Okay, so we've got the coefficient of friction. This was all part A of the question. We're now going to have a look at part B, which says the horizontal force is now reduced to 3 newtons and its direction changed, so it pushes up the slope. So it's pushing up the slope parallel to the slope. Find the acceleration of A, stating its direction. Okay, so let's do a quick redraw of the diagram, and we'll keep the forces that we think are the same as before. So we have the 0.5 G. We're still going to have a normal reaction, and we're going to have this 8 newtons that we've got. It's not 8 newtons anymore. It's now going to be 3 newtons, and it is pushing up the slope parallel to the slope. So there is going to be a 3 newtons like this. Now we need to decide about its acceleration and which direction it is going to go in. So I'm going to start drawing the diagram, and then we'll think about where the friction is going to go. So this 0.5 G, we know from before, when this was theta, this was 0.5 G cos theta, 0.5 G sine theta. And so the thing I'm interested in is which is bigger, the 3 or the 0.5 G sine theta. Those are the ones that are at war with each other. One's trying to go up, one's trying to go down. So if I very quickly work out 0.5 G sine theta, remember that we have sine theta is 0.8. So it's 0.5 times by 9.8 times by 0.8. We get that it is 3.92. 3.92. So 3.92 is greater than 3. Hence, it will be moving down the slope. So friction is going to be going up the slope. Okay, we were doing a quick comparison of these forces. The 0.5 G was bigger than the 3, which means it's wanting to go down, and so the friction is going to be going up the slope. Now, the R that we calculated before, this 9.34, had this 8 sine theta in, which has gone now. So our value of R needed to be recalculated, which means we're going to have a new value of the friction. So if you did want to draw another diagram for this, we could have the R, the mu R, the 3, the 0.5 G sine, the 0.5 G cos theta, and the 0.5 G sine theta. So doing a quick bit of resolving in that sort of perpendicular direction, we can see that R is 0.5 G cos theta, which is 0.5 times 9.8 times the cos of theta, which we've got written as 0.6. So we now have that R is 2.94, which means that the value of mu R, we now know that it is definitely accelerating, so it's going to have reached its maximum. We can say that the friction is equal to mu R. We worked out mu as, what was that, 0.0942. 0.0942 times by R, which is 2.94. Which is 0.276948. So all we need to do now is I'm going to resolve going down the slope using F equals ma. So we have 0.5 G sine theta minus mu R minus 3 equals the mass, which is 0.5 times by the acceleration. So I'm going to do an awful lot of typing on my calculator. That's a 0.5 times by 9.8 times by sine theta, which was 0.8. We're going to subtract mu R, which was 0.276948. We're going to subtract 3, and we're going to divide that by 0.5, and we get that the acceleration is 1.286. If you're ever worried you've done too much rounding in a question, you can just round it to 2 significant figures instead. And we get that the acceleration is 1.3 meters per second squared. It does say to state its direction, so I would say this is going down the slope. So I deliberately did this question. I designed this question in such a way that the direction of the friction flipped around. It was previously about to go up the slope, so the friction was down. Here we had to investigate whether it was going to be moving up or down. We decided that because the 0.5 G was bigger than the 0.5 G sine theta was bigger than the 3, that meant it was wanting to move down. It's the only way that it could be doing that. So I was able to then answer the rest of the question. Okay? So we're now going to have a little bit that is in the textbook and it's in my playlist. I haven't seen a question on it yet, but I still wanted to touch on it just in case it were to come up, but it seems to be a bit more of a rare topic. So we're going to talk about some things with strings. They're called statics, meaning they're in equilibrium, and we'll just read a couple of things about this. So strings. If a particle is attached to 2 strings, it is likely that their tensions are different. Okay, if it's attached to 2 separate strings, unless the diagram is perfectly symmetrical, then they're going to have different tensions. If a smooth bead is threaded on a string, then the tension on both sides of the bead will be equal. Because of the fact that it's smooth, it just means that the tension has to be equal across the whole string. So let's see what this first one is. It says a smooth bead, okay, it's going to be the second scenario, is threaded on a light and extensible string. The ends of the string are attached to two fixed points A and B, which I suppose we could add onto our diagram if we really wanted to, on the same horizontal level. The bead is held in equilibrium by a horizontal force of magnitude 10 newtons, as shown in the diagram. The sections of string make angles of 20 degrees and 30 degrees with the horizontal. Find the tension in the string and the weight of the bead. Okay, so I'm going to add to the diagram that we've got some weight. And the tension from the perspective of the bead that we've got here, it feels like the string is pulling it in this direction and in this direction. You'll notice I've used letter T for both of them because it's exactly the same tension, because it is a smooth bead threaded on a string. So we just need to do a bit of force resolving here. I'm going to start off resolving this tension that we have. Remember, the angle at the top is 30 degrees. So it's going to have a force coming up and a force going to the left. This one is opposite the 30 degrees, so it would be a T sine 30. I don't really like where I've positioned that. Let's see if I can put it somewhere a bit better. Maybe I'll just write it like this. This is a T sine 30. And this is obviously a T cos 30 because it's adjacent. And then maybe I'll do this one over here. I'll do it in a different color. I'll say that this is a tension. There's going to be a force going up and a force going along. This one is opposite the 20 degrees, so it would be a T sine 20. This one's adjacent, so it would be a T cos 20. Now, it's in complete equilibrium, meaning all of the forces are balanced. If you wanted to, you could do another redraw diagram like Miss Wahida Begum would have taught me to do. So the force is going up. We have a T sine 20 and a T sine 30. If this helps. Force to the right, T cos 20, and force to the left, we have a T. Oh, did I put a 30 up there? I did. It just looks like a 20. A T cos 30 in this part. And don't forget, we've still got the 10, and we have the W. So it's just now a case of resolving up and down and left and right. I think the one that makes most sense to start off with first is going to be resolving in the left and right direction, because the up and down has a W, so I think going left and right is going to be much better. So I know from the left and right that T cos 30 plus 10 is equal to T cos 20. So what I'm going to do is put the T cos 30 onto the other side, so it'll be a T cos 20 minus T cos 30. And I can just do cos 20 minus cos 30, because really what I'm doing is I'm factorizing this out, aren't I? So I'll just do 10 divided by cos 20 minus cos 30. 10 divided by cos 20 minus cos 30. And we get that the tension is 135.745, blah, blah, blah. Remember, it is mechanics, so we're going to do that to three significant figures, 136 newtons. But I've done this longer version in case I need it in the second part of the calculation. So for part B of the question, I think I'm just going to resolve in the up and down direction, which means that T sine 30 plus T sine 20 is equal to the weight. So I've already got this tension stored on my calculator. So I'm just going to do the answer times by sine 30 plus the answer times by sine 20. It gives us the weight, and that is 114.300, which is just 114 newtons to three significant figures. Notice how I asked for the weight and not the mass. Weight just means we don't need a G with it. Okay, if it said find the mass, we'd then have to take that and divide it by 9.8, and we get that like the mass is like 11.7 kilograms. Okay, the next question, similar kind of thing. Apart from the fact it says a particle of mass 10 kilograms hangs in equilibrium suspended by two light and extensible strings inclined at 40 and 30 degrees to the horizontal. Find the tension in each of the strings. So this is where it is attached to two strings. It's likely that their tensions are different. If both of these angles were 40 degrees or both 30 degrees, it would be the same, but the angles are different. It is not symmetrical. So the weight is 10G. I will call this one T1. I will call this one T2, and I'm just going to do that same process. So for T2, this would be a T2 sine 30, it's opposite. This would be a T2 cos 30. For T1, when I split it, there is a T1 sine 40 and a T1 cos 40. So if you want to, you can redraw a diagram. I'm going to do a bit of saving time here. I'm going to do resolving up and down and left and right. So if I resolve left and right, it is just that T1 cos 40 equals T2 cos 30. And if I resolve in the up and down direction, I get that T1 sine 40 plus T2 sine 30 is equal to 10g. So it's just simultaneous equations. I just need to figure out a way of solving this. There's many, many ways of doing this. My brain probably goes like this, that T1 is T2 cos 30 over cos 40, and I'll substitute that in here. So T2 cos 30 over cos 40 times that by sine 40 plus T2 sine 30 is equal to 10g. So what I'm going to type on my calculator is this. It's cos 30 sine 40. Have I got that right? Yes. Over cos 40. Too many things that look similar here. Plus sine 30 is 10g. So I just need to type that in and then do 10g divided by that. So it's very, very carefully. Cos 30 times by sine 40 divided by cos 40 plus sine 30. And then I'll do 10 times g divided by that answer. And I get that T2 is 79.89. What's that going to be? Just 79.9. 79.9 newtons to 3 significant figures. But I'm going to leave that on my calculator because I think I need that to figure out what T1 is. So using this, T1 is going to be that T2 value that I've got on my calculator. I'll times it by cos 30 and I will divide it by cos 40. And I get that T1 is 90.31, which is just 90.3 newtons to 3 significant figures. Okay, haven't seen an exam question on this yet, but I wanted to make sure that you were prepared for it just in case something like this comes up. I imagine it would be like a question 1 kind of thing. And then we'll finish off with some things to do with connected particles. So it's the same methods as year 1, but now there's friction and angled forces. Same method means you're going to do an equation of motion twice for each of the particles. Remember, this just means F equals ma. And then typically, it's simultaneous equations. It could be something sort of linked to it. This part about the resultant force on the pulley, I'm actually going to discuss that when we get to part B of this question. Now, I've deliberately done this without a diagram because I think they will usually provide one for you, but I think it's really good practice to be able to construct them yourself. And especially if you're doing further maths, you know that you need to be able to draw these for further mechanics 1. So one end of a light and extensible string is attached to a particle A of mass 3m. The other end of the string is attached to a particle B of mass 4m. The string passes over a small, smooth, light pulley P, which is fixed at the top of a rough, inclined plane. The plane is inclined to the horizontal at an angle alpha, where tan alpha is 5/12. Okay, let's very quickly draw what we know this is going to look like. So we have some kind of plane. It says that A is on the plane. There is a pulley that is at the top, and then B is like this. It says A is held at rest on the plane with the string taut and B hanging freely below P. The section of the string AP is parallel to the line of greatest slope of the plane. Again, that sentence doesn't really mean very much. It just means it's 2D, like we look here. The coefficient of friction between A and the plane is 1/4. Particle A is released and begins to move up the plane. Okay, so it's going to be accelerating in this direction, which means B is going to be accelerating downwards. And it says for the motion, before A reaches the pulley, and giving your answers in terms of M and G where appropriate, find the acceleration of the particles and the tension in the string, and then part B we will come to in a second. So this is kind of the setup of what is going on here. I'm going to add, going back through the question, some of the extra pieces, like the fact that the mass of A is 3m, meaning that its weight is 3 mg. The mass of B was 4m, so its weight is 4 mg that we've got there. We've got that the angle here is alpha, where tan alpha is 5/12. I think we're going to need to figure out sine alpha and cos alpha. You can do that on a calculator, but I do prefer this method. Lots of people say, oh, can I just do it on a calculator? You can. My method I just have a preference for. Any forces that we think we've got missing? Yeah, I think we've definitely got some forces. From B's point of view, the tension feels like it's pulling it up. From A's point of view, the tension feels like it's pulling it up the slope. And of course, there's a normal reaction, and we know that there's friction. It's going to be moving up. As it's moving, it will have reached its maximum value, so there will be mu r that we've got there. And if we want to save a bit of time, we know that mu is a quarter, so on my diagram straight away, I can say that this is 1/4 r that we've got there. I think that's all of the forces, okay? This one obviously doesn't have a normal reaction because it's not touching anything at all. So let's very quickly get our sine alphas and cos alphas because I think we're going to need that in just a second. We know that this triangle that we've got for tan alpha, the opposite and the adjacent. The opposite is 5, the adjacent is 12. The hypotenuse is 13 when you do Pythagoras, but this is just a known Pythagorean triple, which means that sine alpha is the opposite over the hypotenuse and cos alpha is the adjacent over the hypotenuse. So these forces all looking good because they're just going in the direction of movement. Over here, this 3mg is going to need to be resolved so that we have a force here and here. There's my alpha. So this will be a 3mg cos alpha and a 3mg sine alpha. So I'm going to start off with the easy one. I'm going to do for B, I will do its equation of motion, which is just going to be F equals ma. I'll do it in the direction it's moving in. So moving downwards, the resultant force is 4mg minus t, which equals its mass, which is 4m, multiplied by its acceleration. Now, for A that we've got, we do need to be a little bit more careful. If you want to, you could redraw one of the diagrams as one of these types. I'm going to save us a bit of time and try and do it without, okay? Now, I want to figure out what the direction of motion is going to be. So I need to do t minus 1/4 r minus 3mg sine alpha. But because I'm going to need to use r, I think the first thing I need to do is resolve in this direction. So if I resolve perpendicular to the plane, it is not moving in that direction. So these forces are equal to each other. In other words, the r is equal to the 3mg cos alpha. So r is equal to 3mg cos alpha. Cos alpha is 12 over 13. 12 over 13 times 3 is 36 over 13 mg. So now I know that the friction, I've got it on my diagram, is just 1/4 r. So 1/4 of this, you could either do this in your calculator, but 1/4 of 36 is 9. So it's 9 over 13 mg. So I'm now going to do for A, F equals ma going up the slope. The force that we have, or the equation that we have, will be to do with these forces. We have the tension, the 1/4 r, and the 3mg sine alpha. So the resultant force is T minus 1/4 r, which we've just said is 9 over 13 mg, minus the 3mg sine alpha, and that is equal to its mass, which is 3m, times by the acceleration. So I now think we've got enough information to be able to solve these equations simultaneously. So I'm going to try and solve this equation and this equation simultaneously. And the way I'm going to do that is I'm going to take this equation and I will add them. Now, when I add them together, the good thing about adding them is this minus t and this plus t will cancel out. So when I add them, I get 4mg minus t, and then from the next part, I get a plus t minus 9 over 13 mg minus 3mg sine alpha is 5 over 13. And then on the right-hand side, I have a 4ma and a 3ma, which is going to be a 7ma in just a second. So, great thing is that these cancel. I then have, on my calculator, I will do a 4 minus 9 over 13 minus 3 times 5 over 13. 4 minus 9 over 13 minus 3 times 5 over 13. Oh, I didn't know why this is a 7. That's obviously still a 3, isn't it? I jumped the gun there. So when you do 4 minus 9 over 13 minus 3 times 5 over 13, you get 28. You get 28 over 13 mg equals 7 ma. The m's cancel. We then divide by 7, and we get that the acceleration is 4 over 13 g. And it did say it's okay to leave our answer in terms of g there. Okay, we still need to now find out the tension in the string. Well, we found out the acceleration. I think we can just use this equation to now find out what the tension is. So if I take this one here, I'll put a little star next to it. If I rearrange that equation, I would say that the tension is equal to 4mg minus 4ma. Add the tension to that side and you're subtracting the 4ma. So it is 4mg minus 4m times by the acceleration, which is 4 over 13g. So I'm going to be doing 4 minus 4 times 4 over 13, ignoring the m's and g's that we've got there, which is 36 over 13 mg. That is what the tension is in the string. And it did say it's okay to leave our answer in terms of m and g where appropriate. Acceleration will never have m with it. Tension will have m with it. It makes sense that if something is heavier, the tension will be stronger. And then the last thing we're going to do is find the magnitude of the force exerted on the pulley by the string. So I'm now going to jump back to this box that we've got here. Now this is now going to be forces drawn from the perspective of the pulley. It feels like this string and this string are pulling on it. So from its point of view, it feels like there's tension here and here. The tension is the same on each side of the pulley because the pulley is smooth. So if I do a quick diagram to think about what's going on, I have an alpha down here. This angle at the top is a 90 minus alpha. And I'm going to try and find out what happens with these T forces when I resolve them. I'm going to try and resolve each of the T forces into a force like this and a force like this for the top one, and a force like this and a force like this for the bottom one. And the reason I do this is because these ones will just cancel, and then the ones that are acting on the pulley are these two blue ones that we've got here. So this angle that we're looking at, this angle here and here, if the top angle is 90 minus alpha, each of those angles is 90 minus alpha. And when we resolve them and find out what these two blue forces are, well, it would be a T, and it's adjacent to the 90 minus alpha, so it's a T times by the cos of 90 minus alpha. It would be a T times by the cos of 90 minus alpha. And then for the other string, it is also a T times by the cos, not 90 minus alpha, 90 minus alpha over 2. Excuse me, it is 90 minus alpha over 2 because it is going in the middle of this angle, so it will be half of that. So it's 90 minus alpha over 2. T plus cos of 90 minus alpha over 2. And because there's two of them, we can just write this as 2t, the cos of 90 minus alpha over 2. So our last part, this wasn't really B, was it? This was A continued. Our last part of the question is to do B, which is to just, you can quote this from memory. It is to work out 2t cos of 90 minus alpha over 2. So I'm going to quickly figure out what alpha is. Alpha is the inverse tan of 5 over 12. So the inverse tan of 5 over 12, that's like 22.6 degrees. So I can now actually just go straight on to doing this calculation. It's going to be 2 times by the 36 over 13 mg times by the cos of, well, let's do 90 minus that alpha that I've got on my calculator and divide it by 2. That is 33.6 blah, blah, blah degrees. So I shall do the cos of that. I shall times it by 2. I'll times it by 36 over 13. And it's okay to give this as a decimal rather than as a fraction because we're not going to have this as an exact fraction. This is 4.61 mg to 3 significant figures. If you wanted to, you could multiply it by 9.8 and you could have said that it is 45.2 m, just giving it in terms of m, and that's also to 3 significant figures. So either of those answers would be correct for this. This is kind of a strange part to do with this, but I always just add it in just in case they ever ask it. It's a good little formula to memorize, and hopefully that was a good overview of everything to do with forces. Now, I suppose I should say that this isn't going to be enough to teach you. This is really just like a revision of these kinds of concepts that we have here, and they can always ask you things in unusual ways that feel different. With mechanics, it is so important you truly understand what forces are, how they're behaving, and how they're working, because it's often not that easy to replicate what's happening. You really do have to understand what is going on. But I do hope this was a good revision video for you, and I hope to see you in another chapter summary very soon.